Hello, in this module we are going for illustration with R for analytical studies. Analytical studies can be divided broadly into three ways. One is cross-sectional study, another one is case control study, and third one is cohort study. Here this term cohort we will use here, and for cohort study one indicator is called attributable risks, and attributable risks we will illustrate in this module. What is the importance to consider attributable risks, how to prepare data to calculate attributable risks, and how to make functions for analysis attributable risks, and later on statistical inference about attributable risks we will see here. In this module we will use the library called Attributable to analyze data to calculate the attributable risks. Attributable risks is a indicator where disease exposed subtracted by disease unexposed divided by disease exposed is used to calculate the attributable risks. It is suitable for cohort study where a group of people followed for long times, and once they followed for long time, some of them follows or exposed to some causal and some of them are not exposed to some causal, and after that when they exposed and unexposed, if these people get the disease, then the effect of exposure with respect to effect of not exposure calculated as attributable risks. For example, we want to conduct a study on cohort of people who followed for longer than 20 years, and among them some of them started taking smoking and alcohol, and after 20 years those were smoker and those were alcohol takers, some of them developed cancer, lung cancer, and the same cohort, those were not smoker and not alcohol taker, among them also some developed lung cancer. Now questions may rise, what is the attributions having cancer on smoking and alcohol? So we can, from this cohort we can find out how many people were exposed with smoking and alcohol, and among them how many were having cancer, lung cancer, subtracted that value by those were non-smoker and non-alcohol taker but having lung cancer. This value can be divided by those were non-exposure with alcohol and smoking but having disease. That value as a ratio will give us the attributable risks, and that attributable risks can be used, can be concluded as influence of alcohol and smoking on lung cancer. Here we will see about the attributable risks, function to compute attributable risks, and statistical inference about attributable risks from an example data. Reference about attributable risks can be cited from here. Now see about the attributable risks. So let probability of disease is defined at probability of P of D, and probability of risk factors from sample population, those are having exposed with risk factor defined as probability of F. The conditional probability of disease among those with the risk factors is defined as probability of D given F, and probability of D given F complement is given as conditional probability of disease among those without the risk factor. Probability of P given D is the conditional probability of the factor being present among those who are having disease, and probability of P of F given D complement is the conditional probability of the factor being present among those not disease. So if we divide probability of D given F by probability of D given F complement, then we will get the relative breaks, and that is probability of disease among those with risk factor by probability of disease among those without the risk factor. So that is also can be seen as probability of disease among exposure with probability of disease among non-exposure. So that will give us the relative breaks. There is a good relation between attributable breaks and relative breaks. Attributable breaks and relative breaks both are useful for cohort study. Now attributable breaks is defined as probability of D subtracted by probability of D given F complement by probability of D, that is probability of diseased people minus probability of disease given who was not exposed with the disease or risk factor of the disease by probability of disease. Alternatively, it can also be expressed this attributable breaks as probability of F, that is those are having risk factors, multiplied with relative breaks, that is RR minus 1 divided by probability of F, that is probability those are having risk factor exposure, multiplied with RR minus 1, the same component used in upper side, plus 1. In context of relative breaks, the attributable breaks can be defined as probability of F given D multiplied with RR minus 1 by RR. So there is a close relation between relative breaks and attributable breaks. In other module we have seen how to calculate the relative breaks and how to use different confidence interval and how to prepare contingency table to calculate relative breaks and how to make statistical inference about relative breaks we have seen. Here in this slide we will use data available in library, and library attrib breaks we will use, but the data set chapter.dat will be used to analyze the data and to illustrate the inference about the attributable breaks. This library attrib breaks is dedicated for to compute the attributable breaks. This data set chapter.dat is having long observations, is having more than 1500 observations, but to see this initial few observations we put it as chapter.dat, within bracket we had put 1 to 10 and comma, so that is showing us the first 10 observations in the data set, and it's showing that the data set is having observation of variable HBP that is coded as 1 or 0. So if high blood pressure is present, then it coded as 1. If high blood pressure is absent, then it coded as 0. DM is also given if diabetes mellitus is there of those patients, so it is denoted as 1. If diabetes mellitus is absent, then it is denoted as 0. ISD also another high per density is given as 0 and 1, and here since attributable breaks is there, it's coming as a useful of cohort study, but here we are using these cases as a presence or absence. So, and another important thing for analytical studies, the matching, and for how to do the matching analysis, for that we will go for another module, but here matching ID is considered here as a matching ID 1, 2, 3, 4, 14. So matching will be used here for next step analysis. I will not go into details about the matching here, we will go into others module for matching. So anyway, this is the data set on attributable breaks library, and we will analyze to get the attributable breaks from this data. Calculating the attributable risk functions. Before that, we are going to see the end of this data set. To see it, we are putting chapter.dat with 1500 to 1510, and here the observation from 1500 to 1510 is given, where again HPV1 is present in these individuals, DM were not present in these individuals, and they are coded as 1. So earlier we have seen these cases was given as 0, so here this individual or R belongs to cases, and again their corresponding matching ID is given, and it started from 178 to 188. So we'll go next one to prepare a table from this data set. To prepare the data table about the HPV, how many were having HPV and not, and how many were having belonging from cases and not, we are using a function called table, and this output of this function table is being assigned to count, and where table is there, after that we are putting the in parenthesis chapter of this HPV. So variable HPV and chapter.dat of cases is considered. So as a table we can see first row showing at HPV 0 for the cases who were absent, that is cases 0 is considered here, that is 559. So those who were not cases, among them high blood pressure were with 559 individuals, and among the cases high blood pressures were absent to 384 individuals. Those who were having high blood pressures but still they were not cases is 763 patients, and those who are having high blood pressure but still in cases it is 938 individuals. Now the function to compute the attributable rates, this example 1 is assigned here with the attrib rates, where cases follows to exposure of HBP is considered here, comma data equals to chapter.dat is considered to calculate the attributable rates. Once we assign these functions into example 1, and after that we calling example 1, we are getting that degree of freedom of this analysis is 2643, obviously because we are having huge number of observation here, and coefficient, standard error, lower 0.95 confidence interval and upper 0.95 confidence interval is coming here. So as a point estimates of attributable risks, it's coming 0.31 and with standard error 0.04, having lower and upper confidence intervals from 0.22 to 0.40. It shows that those who are having exposure with high blood pressures, that is those who are having positive high blood pressures, among them the cases subtracted those who are not having high blood pressures, among them cases divided by those who are not having high blood pressure, among them the cases is basically 0.31. So this way it can conclude that attributable risk is quite low, lesser than 1 in this scenario, and it can also be concluded that is 31% chances is there, exactly 31.30% chances is there for having disease with high blood pressure. Now coming to functions to calculate attributable risks with match cases. So when we are putting these functions match.id equals to 1, so we found that the ID 1 was matched with 1323 ID. Both were having high blood pressure 0, both were having diabetes mellitus 0, both were having ISD 0, that is these three factors were absent among both the groups. Only different between these two ID was one was belonging from cases, that is 1323, and another one was, that is ID 1 was belonging from controls, that not cases. So once we match them, after that we try to find out so this is the results. Before that we assigned it this example as a example 2 with the function attributes and cases with strata with matching.id, and plus exposure of HBP is considered here. So once we consider the match.id, so cases and control has been matched with respect to diabetes mellitus with respect to ISD and with respect to HBP. Now once this is matched, then we try to find out the influence of HBP, high blood pressures, on cases for the data chapter.dat. So this is the meaning of these functions. Example 2 assigned as attributes with cases follows to strata of match.id plus expose of HBP and data equals to chapter.dat is given. Once we call example 2, then as a result we are getting total number of observation as 2644, where coefficients for attributable risk coming 0.33 with standard error of this estimate as 0.04 and lower confidence interval as 0.41 and upper confidence intervals as 0.24. So here it is to be noted that this estimate is quite different in comparison to when we have not done the matching. So in this data set, in these functions, we have considered the matching ID as strata, and initially we didn't consider the matching ID. There we are getting attributable risks as 0.31, but now we are getting attributable risks with 0.33. So influence of other factor like DM and ISD has been removed, and only the influence of HBP is present once we done the matching here, and as a result the attributable risks increase. Now another variable here we are considering the HBP and DM, high blood pressure and diabetes mellitus we had considered here, and this assigned as example 3, but the function attributes cases follows to expose of HBP plus expose of DM is considered, as data equals to chapter.dat considers. When you are calling example 3, as a result we are getting attributable risks is coming 0.36 with corresponding confidence interval. In this module we have used attributes library in R to compute the attributable risks. In addition to that, we also see how to prepare table and the computational power to calculate attributable risks. In this illustration, we had used one example. The same kind of example can be also used, or you may use this attributable risks with these R code in others suitable problems similarly with these objectives. I hope you enjoyed this module and it will help you further for your work on attributable risk analysis.